All right, let's dive into linear models. So linear models make a prediction based on a linear function of the input features x. So if we have a feature x, vector x, this vector x has p variables. This function f has also weights, and it will have basically p plus 1 weights. It will have to learn a weight for every dimension of x plus what we call a bias or an intercept like this. So if we have a bunch of points like this, we want to learn a function f. Say this is x, this is one dimensional. Then this function here has a slope w1 and an intercept, which is where it intersects with y, which is w0. Right. So this function f here is totally described by this intercept, the bias, and this weight w1 here. Right. So basically, this is a class of functions which will always be linear, and where the goal is basically to find the values of this vector w, to find the weights based on data, according to some loss function L. So this loss function basically tells us how good or how bad this solution is. Maybe this is a good solution, maybe, I know, this could be a bad solution for these points, right? And the loss function is some way to compute whether our function fits the data or not. Right? So we say that given the data x, we want to learn the weights of this linear function f according to a loss function. Now, depending on what this loss function is, there exist a bunch of different algorithms. And we'll discuss some of them, like least squares or Ridge and Lasso or logistic regression and so on. And they're basically all similar, but they use different loss functions, and that means they also need different ways to optimize these values w. Now, this class of linear models is very powerful and especially fast. So if you have a large data set, then linear models are definitely a good idea, especially if they also have many features. They're not so good whenever you have a data set which has a very complex structure and it's only a few features, because it's a linear line, it cannot really learn complex functions. But if you have high dimensions, then you have a lot of degrees of freedom, right? And so in a high dimensional space, even a linear model can learn complex relationships between the features. We'll get back to that. Now, they're also very powerful because they can be generalized to learn nonlinear patterns. This is a more general class of models called generalized linear models. There's different ways in doing this. So first of all, we can augment our features with, for instance, polynomials. So if you have feature x, what we can do is we can basically add a function x squared and x to the third and so on. So we add variables to our data set, we add columns to our data set, and if we learn a linear model in this higher dimensional space, we can learn more complex functions. We can also transform the features according to some distribution, like Poisson, which is very popular. There are some others as well. And actually, I think Poisson linear regression is one of the most used algorithms in practice. And in the next lecture, we will see kernelization. We'll see that some of these linear models, especially support vector machines, can be kernelized. So we can change how these algorithms work so they can also learn nonlinear function, even though the weights themselves are still a linear combination of features. Okay, first, linear models for regression. So in this case, again, we want to learn a linear function f through these data points. This is a one-dimension x. In this case, these weights are written w, and we call these the weights or the coefficients, and there's W0, which is the bias or the intercept. Right? If we, for instance, look at these data points, and we fit this, we see that the weight is 0.39. That means for every time that x goes up 1, y goes up 0.35. Right? That's the slope of this function. And the intercept is minus 0.03. That's where it crosses the line here. Now, this model assumes that the errors of this function are non-distributed. So basically, if you would project that, then basically we assume that the errors of this function are non-distributed around the prediction. Right? So whenever you have to make a prediction, we predict the mean of this function. So it's just an assumption that the model makes. The first way of doing this is called linear regression, or ordinary least squares. The idea here is that we can compute the error of this function using the sum of squared errors. What we do is, so say that the blue points are our training points. We fit a line through there, and then the residual, or the error, of each point in our training set is the difference between the actual value and the predicted value. Right? This is the error that this function makes, and this should be as small as possible. Now, because these residuals can be positive or negative depending on which side of the line you follow, we want to square these errors. So it's always positive, and the loss goes up with every error that we make. It's a very simple way of doing it. Right? So our prediction here is y hat n, which is computed as the top product of our weights and our inputs x plus a bias. Right? So we see that the weights are a function of the loss function. So the loss function is a function of our weights. So if we change the weight, we get a value for the loss function, and basically we want to find the set of weights which minimizes this sum here. This is the sum over all the points in our data set. Now, ordinary least squares is a convex problem, right? It's a sum of squares, so this will be convex and is therefore easier to solve. And in fact, there exists a unique closed form solution for this, which looks like this. So x is our training set x, and we can compute the optimal weights using linear algebra, basically by computing x transpose x, then inverting that, and then times x transpose y. If you want the values for the bias, you can do that by adding a column of ones, basically, before you have the values x. And if you then compute that, then the W0 comes out of that. This is nice, right? So we have a closed form solution, so we can actually solve this exactly. The problem is that this is kind of slow for many machine learning applications. The reason is that this matrix here, x transpose x. So if this matrix has n rows and p features, this has a dimensionality p times p, and we have to invert this matrix. Right? That means that the time complexity is quadratic in the number of features. So the complexity is p squared and n number of instances. So that's one problem, right? So whenever our dataset is large, this becomes quite expensive to compute. Also, this only works if the number of data points is larger than the number of features. Whenever you can't do this, so whenever you have like a very high dimensional data set with few examples, or you have a very large data set, and it just takes too long to compute this closed form solution, you can use instead gradient descent. So this will be useful whenever you have very large, very high dimensional data sets. There are also some cases where you cannot compute this guy because your data has some deficiencies, but then still gradient descent will work. So there's two ways of doing this: convex optimization and then gradient descent. No matter which one you use, least squares has a problem that it very easily overfits the training data. And you will see that by, if you look at the coefficients will be very large, which means that if you have a variable x0 and this is y, if the coefficient is large, then in this direction of x0, this function will be very steep. This function of x. This means that whenever you have value x and you have a value that's very close to it, then the outcome of the function will be different. And this is something you typically don't want. If you have one observation and you have like a very similar observation and the output is completely different, that's typically not what you want in a machine learning model. Unless your data just happens to be that way, right? Also, ordinary least squares has no way to control this complexity. Right? So whenever you find an overfitted function, there's no, well, in the model itself, there's no way to resolve this problem. So that's the reason why we typically never use ordinary least squares in most applications. But let's first see how we can solve this with gradient descent, because this will be very useful. Now, to do gradient descent, we start first of all with a first random filter weights. Depending on the algorithm, you can do this in different ways. For linear regression, we typically just use some random weights. If you have a large neural net, typically you use very small random weights. And then we have to, so if you choose some random value x, this corresponds to, so this will be W0, this will be a loss function corresponding to W0, right? Now we want to know whether we should increase or decrease this weight. The way to do that is to compute the gradient of this function in this point. Okay. Now, the derivative of the sum of squared errors with respect to W1, so remember sum of squared errors was something like 1 y minus y hat squared. So derivative will be, and w occurs in here, right? So will be minus 2 times the sum of what remains here. And because in here wi occurs with, as part of the sum, occurs with w, we have to add that value x and I at the end here. Right. So intuitively, this means that if a feature colon I is associated with big errors, then the gradient will be large. Right. So this means that whenever we have an error, if the feature has a large value at that point, then we may want to reduce the weight of the feature and vice versa. Now, the way to then update the weights is to update all the weights slightly. So intuitively, what you can do is you can take W0 here, you compute the gradient. This tells you that you should move to the right. So x0 should increase. And so you could do a step, and you could actually take a very large step and end up somewhere here. But it's typically more useful to attenuate this by some factor eta here, which is called the learning rate. because we've learned from experience that if you take many small steps, this is typically better than taking very big steps, because if you take big steps, you can more easily get stuck. So then the final update rule will be that the next value for W will be our starting position as minus the gradient. So the gradient here is negative. So we have to go minus times negative is positive. So we have to move in the positive direction. And the step size is eta times this gradient here. So this brings us to the next value here. And then we repeat. And we keep repeating until we converge or after a number of steps we stop. Now, before we can use gradient descent, we have to choose a number of important hyperparameters. First of all, the learning rate. So in this simulation here, I have a convex loss function, and I have to choose a learning rate. In this case, learning rate is 0.06, and I can see I will converge in about 6 steps. Now, if I make my learning rate smaller, you'll see that the updates will also get smaller, and it will take longer before we end up in our optimum. If our learning rates are really small, we may not even converge. So we will do a number of steps, and after we do all those steps, we still haven't converged. So if my learning rate is too small, I will not find my optimum efficiently. Right. If I set it correctly, then of course we can find the solution faster. And if we magically know the best one, or we tune the learning rate according to some validation set, then we can find a value which very quickly converges. Now, if my learning rate gets larger, then it's not a disaster. It will just take a step like that. Oh, that's too far. So if the learning rate is large, it will again do this kind of zigzag pattern. So update like this, go down here, update like this, and so on. So every time the step gets smaller because the gradient gets smaller. Right? So here we have a very strong gradient, so we take a big step. Here the gradient is a little bit smaller, so take a smaller step, then it's even smaller. So that's why these steps get smaller and smaller, because also the gradient in the next point gets smaller. Right? Now, if my learning rate is unlucky, I can sometimes get stuck. Like if I do this. So now I'm not converging. If I do this, I'm just bouncing up and down all the time, so I will never find a good optimum. And if my learning rate is really too large, then I will even diverge. Right? So now, the more I train, the worse my solution gets. Right? So this sometimes happens with deep neural networks. If your learning rate is too large, your network will just diverge. So that's not nice. So then you have to reduce the learning rate. Now, one way to avoid such issues is to use something called exponential decay, or learning rate decay in general. So one way to do this is exponential decay, which basically means we take our previous learning rate and we multiply it by some fixed value, constant, which is defined by the exponent of minus k times s. S is a step, and k is the decay rate. So every step, this value gets larger, and so the learning rate gets exponentially smaller. If you can see the effect here. So now, even though I have this catastrophic learning rate at the beginning, it's not so bad, because in the next step, this exponential decay will make the learning rate smaller, and so I'll find a good solution here. It's not always ideal, right? So if I have the learning rate which was optimal, like here, then we have a good solution, and my exponential decay will then cause non-convergence, right? So you basically need to tune both the decay and the learning rate. But in general, the exponential decay makes your makes the gradient descent more robust against having non-ideal learning rates. Another way to do this is called inverse time learning rate decay, which is basically our initial learning rate times 1 over 1 plus ks, k again being the decay rate and s being the step. Now, both of these require you to choose a decay rate, like 0.01 or something like that. Right? So it's another higher parameter that you have to choose. Now, these are just some options, and especially for like linear regression, this is fine. You don't need much more. Later on in deep learning networks, we will see many more techniques to control this learning rate, and especially adaptive techniques. So these are techniques that change the learning rate according to how much your loss changes. So if you have an update or a step in which the loss goes down by a lot, then typically you want the next step to be even larger. And so there are different adaptive techniques that we'll discuss in due time. Now, a question I often get is, won't this get stuck in local minima? Well, yes, that's true. First of all, for linear regression, this is not a problem because we have a convex function, so we cannot get stuck. There's only one minimum. But in general, if, for instance, we have deep learning networks, this surface here, this is the loss function, this surface will become very complex, and there will be many local minima. Now, even though you can get stuck in local minima, this is not always a disaster, because if you have many, well, especially if you have many dimensions. Say, for instance, in 2 dimensions here, you get stuck in this local minima. You can't get out of it. But if you have a 3rd dimension, maybe in the 3rd dimension, you can still go down. And if you have a 4th and a 5th, and you have 10,000 other dimensions, then it's very likely that at least in one of these dimensions, you can still go down. And then, yes, you will go down until you end up in some local minima, but because it's such a high dimensional space, you will find a local minimum which is very close to the true optimal minimum, the global minimum. So if you have a model which has a lot of parameters, like a neural network with lots of weights, then you will still get stuck in local minima, but that local minimum will probably be very good, right? That's the intuition. Another way to intuitively explain how gradient descent works is by this image by Andrei Karpathy. So imagine you are this guy. So we cannot see the entire surface, right? This surface here is unknown to us. We could evaluate every possible weight, but if you have 1,000 weights, this becomes computationally infeasible. So you can basically only evaluate some points, and hopefully as few as possible. So you want to know in which point you want to evaluate next. And the way to do that is to compute, of course, a gradient, which can intuitively be understood by being this guy with a blindfold. You can't see everything, but you can like feel around what your local gradient is, and then do one step downhill and keep doing that. Now in 2D, you will get lots of local minima, but in like a very high dimensional space, you will always find a way down to a good minimum. Right. There's different variations of gradient descent, which are important to discuss. First of all, there's stochastic gradient descent. So the idea there is that you will still compute gradients, but instead of computing the gradient using your entire data set, you will do it on a single point I. So if you remember, our gradient descent was defined by, well, the updated rule of gradient descent was defined by this function. And computing this gradient means using all the data in your data set to compute the gradient, to evaluate the loss function. And you can break this down into the sum over all your data points n. the sum of the individual gradients for every point. Right? So your total loss is the sum of the losses of every point, as we've seen before, right? So you could write this like this, divided by n. Okay? Now, stochastic gradient descent, we basically remove this sum, and we base our update of our weights only on the current point we're looking at. Right? So every time we look at one point, compute the gradient for this one point, the loss, we compute the loss and the gradient for this one point, and then we update the weights. Now, this gradient will of course, be noisy because it's based on a single point. And if you would look at what this does, so here we have the same starting position. Gradient descent will find exactly the direction to go downhill. So if you're on this contour, this is the best way to go. And then you're on this contour, then you're the way to go. So, and then you compute the correct gradient every time, and you'll get there in a number of steps. Now, stochastic gradient descent won't be able to compute this because it only knows one data point, but it will take a step which is hopefully somewhat in the right direction, and we'll do this many, many times. So this will definitely be more noisy, but because every step takes much less compute, right? To compute the gradient on one point is much, much cheaper than computing the gradient over all the points in your data set. You can do many of these zigzag steps in the time that you can do one gradient descent steps. Right? And so that's why stochastic gradient descent typically works faster than a gradient descent. And also, because it's so random, it also is less likely to get stuck. Okay, that's stochastic gradient descent. There is one method in between, which is called mini batch stochastic gradient descent, which does the same thing, but instead of looking at one point, it looks at b points. So this is similar to gradient descent, but instead of looking at all your points n, you only look at the batch b of points. B is simply something like 32 or 64, something like that. Right? So it's a smaller number of data points, but they should still be small enough so you still get the benefits of stochastic gradient descent while having a bit more direction than stochastic gradient descent. Another approach, which is useful especially for linear regression, is called stochastic average gradient descent. So the idea there is that we do compute a full gradient, so we go over all the points n, but instead of computing all the gradients for every single point, we do it only for one random point I, and all the other components, so the gradients of all the other points, we keep them as they were before. Right? This is also called an incremental gradient. So we don't completely replace this gradient, we only replace one component. We only update the gradient for one random point in our data set. This is a smoothed version of stochastic gradient descent, right? Which is more smooth. It works nicer, and especially for linear models, this is one of the best techniques you can use. Now, how can we do this in practice? So linear regression can be found in the in the linear model package. So in this case, we will evaluate it on the Boston housing dataset. There's different implementations we can use. So we can use linear regression. This uses the closed form solution. If we want to use gradient descent, we have to use the SGD regressor with as a loss function the squared loss. Right. So again, if you have a smallish data set, by all means use linear regression. If you have a very large data set, it may be better to use the SGD regressor with squared loss if you want to emulate, at least if you want to emulate ordinary least squares, but we'll see some better variants in a few slides. All right. Okay, so this is our first result using linear regression on a real data set, and we see that the coefficients that come out of ordinary least squares are quite big. So we have 2,900, we have 1,200, minus 2,200. So these are all very big coefficients. If you look at the test score, we can see that the test score is quite bad. So this is R squared. So this is, we'll talk about different evaluation functions later. But this value here should be ideally 1 and should be also ideally larger than 0. 0 means it's basically predicting the mean. So you want to be larger than 0 and as close as possible to 1. So we see that for this model, the training set score is high, test set score is much, much lower. So this model is very likely overfitting. One way to solve this overfitting is to change the loss function to require that the weights be small. We can do that by adding a component. This is our original least squares loss. We add a component which computes the sum of the squares of the weights times an attenuation factor alpha. This means that whenever you have a model with large values for the weights, the loss will increase a lot. If you find a model which is equally good but has smaller weights, then this is preferred. We'll have a lower loss. Right? So this is one way of regularization. It explicitly adds a factor to the loss function that causes the model to avoid overfitting. And it's called L2 regularization because it uses the L2 norm, which is the sum of the squares of the weights. Now the strength of this regularization can be controlled by this alpha hyperparameter. Increasing alpha, having a larger alpha, means more regularization. It means this factor gets a larger influence on the loss. Right? If you would set alpha to 0, then this thing will disappear and we're back to ordinary least squares. If we set alpha very large, then we'll add a very strong focus on making the weights small, and then we'll find some solution in which the weights are explicitly small. Regularization is also called shrinkage, by the way. So that's also why we call it the shrinkage parameter. Typically, just called alpha, or the regularization strength. Now, this loss function is still convex and still differentiable. So we can basically use the same techniques to solve it. So first of all, we can use a closed form solution, which basically looks very similar to the one for least squares. It just adds this component here. This is also called Kodetsky, well, it uses the Kodetsky decomposition. So whenever you use an algorithm, when you see Kodetsky, it means it uses a closed form solution. We can also use gradient descent. We can use stochastic average gradient descent. We can also use something called conjugate gradients. This is again a variant of gradient descent, which tries to smooth gradient descent by by changing each update so that it goes in the same direction as previous updates. So if you have one value W S and you update here to WS plus 1, and then computing the gradient would, for instance, push you this direction. Instead of doing this zigzag, you there's some combination of this guy and this guy so that you will actually go more like this direction. Right? So this is conjugate gradient descent. It's another variant of gradient descent which ensures that your gradient updates won't zigzag so much but will ultimately still find the optimal solution. Um, in practice, you should probably use Scholastic or the closed form solution for smaller datasets and gradient descent for larger datasets. And to choose the gradient descent method, the most popular choices are the conjugate gradient or the stochastic average gradient. You can do this in practice by breaking out Ridge from scikit-learn. If we fit it with the default parameters, so we're not changing alpha, we just use the default alpha, which is alpha equals 1. If we fit this and we look at the coefficients, we can see that indeed these coefficients are much, much smaller than with least squares. We also see that the test set score is a lot higher and the training set score is a lot lower, right? So compared to what we saw before, so here we had large weights, small test set score, 61, and with Ridge, we can see that coefficients are smaller and test set score is a lot better. Right? So this is definitely overfitting less. Now the question is this the best solution, or can we play with this alpha parameter to find an even better one? This is a simulation, so if we take all of these coefficients, so minus 1.4, minus 1.5, and so on, and we would plot them like this. Let's set alpha to 1. So here we have minus 0.14, minus 1.5, and so on. So these are all our weights plotted next to each other, right? Now we can see that if we reduce alpha, the weights get larger until we reach alpha 0, which is identical to least squares. So least squares has lots of weights with large values, and the score, the tested score, is quite low. Increasing alpha makes the weight smaller and makes the test score increase. What happens if we make alpha even larger? We'll see that the weights will still get smaller and smaller and smaller, but we will also see at some point that our score will go down again. That means we are underfitting, right? We're restricting the model so much, it doesn't have much freedom anymore in changing the weights. So we're constraining it too much and the model will be underfitting. If we plot alpha for every value versus the score, the test score, we can see that we find an optimum around 0.2-ish. Right? So if alpha is smaller, this is more like least squares, we can see the low test score and a high training score. So here it's overfitting. Increasing alpha leads us to our sweet spot. So here the fit is perfect. It's neither under or overfitting. If we make alpha too large, we can see the test score goes down again. So here it's underfitting. Right? So here the model is too simple to learn the data correctly. So we have to reduce alpha to find a good solution. Right? So in any case, you have to tune this parameter alpha to your data to find the best model. Now, I would preface it by saying that next to alpha, there are other ways that you can reduce overfitting. One thing you can do is just add more training data. Right? If you have a lot of data, then the model is less likely to overfit, and regularization becomes less important. So in this case, we have two algorithms. We have Ridge, which is a blue line, and linear regression, which is a red line. So we see that if the data set is small, Ridge does a reasonably good job. Linear regression is completely overfitting. I mean, the R-square score is less than 0, which means it's really bad, right? So it's completely overfitting. If the dataset gets larger, we get a better performance, and if the dataset is large enough, linear regression will be as good as Ridge, right? Even without having this regularization. Now, in principle, we cannot magically summon up more data points, so given a data set, it's always still good to tune alpha so that you find the optimal fit for your data. Another thing you can do if you have the option is to remove features from your dataset. So if your dataset has a lot of unnecessary features, it makes sense to remove some of these, because having fewer features means having fewer weights, and that means there's less likelihood of overfitting. Right? So if you have a dataset, you can do feature selection, or you can use a low dimensional embedding like PCA, and in that case, it's less likely for the model to overfit. Of course, it is likely that you throw away information, which is bad, or that you remove so much features that the linear model is too simple and it will underfit. Right. Another thing I have to say is that scaling the data typically helps, and it changes the optimal alpha value. If you would look at this curve here, if you would scale, if this is the curve for non-scaled data, then scaling the data would make this curve much flatter, maybe something like this. Right? And then having the optimal alpha doesn't really matter so much. But of course, given a data set, you don't know that. In any case, it doesn't hurt to scale your data. So by all means, if you use linear regression, scale your data. It typically improves your modeling, and it also makes it easier to tune your alpha parameter. But do keep in mind that if you scale your data, you should retune alpha, because the optimal value will change. Another way to solve this is by not using the sum of the squares, but using the absolute values. Right. This is called L1 regularization because it uses the L1 norm. Now, this method, this loss function, is called lasso. This stands for least absolute shrinkage and selection operator. It's absolute because it uses the L1 norm, so it uses the absolute value. It has shrinkage because we have a shrinkage parameter. We can control the amount of shrinkage. And it's also a selection operator because, as it turns out, if you use this, many weights will be exactly 0, which means that if the weights are 0, then that feature has no role in the model, and you can just ignore the feature. The model ignores the feature. Right? We have, again, the same parameter alpha to tune. This controls regularization, so again, we have to find the sweet spot. Now, this loss function is no longer strictly convex, right? So it's still convex, but it's no longer differentiable because this function here is not differentiable. If you would plot that, so we have W, then this loss function would look like this. This is the absolute value in terms of W. So it doesn't have a gradient in this point. So we can there's no closed form solution anymore, and we cannot easily use gradient descent here either. Now, there is a variant called coordinate descent, which we can use instead. Now, first of all, let's analyze what happens to the weights to see if they really get 0. Right? So let's start with, again, let's start with alpha 0. So this is our least square solution. Again, we have a low score. If we increase alpha a little bit, we will see that already a number of features get to 0, which means these features are completely removed from the model. And our score goes up. And so even though this model only uses 1, 2, 3, 4, 5, 6, 7 features, 7 weights, the score is much better than the least square solution. Now, if alpha gets too large, then of course, again, you will see that more features become 0, but it will also, the test score will also get lower, so it will start underfitting again. So this model only has 2 weights, but the score is lower than we had previously. So this model is overfitting. We've constrained the model too much. We forced it too much to set weights to 0, and now it doesn't fit the data anymore. Right? So we have to tune this alpha again to find the sweet spot. Now let's take a closer look at coordinate descent and why Lasso sets so many weights to 0. So coordinate descent is quite different algorithm actually. So what it does, instead of optimizing the weights, so say the two-dimensional space W0, W1, gradient descent would basically compute the gradient in both directions and then update accordingly. Coordinate descent is different in that it only updates one weight at a time. So say it selects, for instance, first W1. So then it updates W1, and it doesn't just take a step, it will find the optimal solution starting from here in the direction of W1. So if you would look at this contour, so these contours here are a loss function. You can see it's convex. And we will find the point in this line which has the lowest value, which is here. So it will completely optimize W1 in one step, but only for this value of W0. After that, we will find the optimal value for W0, given that we have W1 set to this value, so we find this function. And we keep doing that until we find the optimal solution. Right? Now, because we only look at one variable, with computing this gradient is faster. Right? So every single step in itself is faster than a gradient descent step. Also, we don't have to choose a learning rate. But because it has this zigzag pattern, it may still converge more slowly, and because it's also an iterative technique, it cannot be parallelized. But for Lasso, this is the best we got. Now, how does this work with Lasso? So remember that Lasso is basically the loss of the sum of squared errors plus this L1 component, attenuated by this alpha value. Now, if you would look at one weight Wi, then the loss for this Wi is, again, it's the loss of the sum of squared errors according to Wi plus alpha times this value. Simply the sum here disappears, right? So we want to do this for one Wi at a time. Now, this L1 term here, like you see, is not differentiable, but it is still convex, which means we can compute the subgradient. So if you don't know subgradients, just click this link to get some of a more understanding. But let me just quickly explain the basic. So if we have a Wi here, because we have the absolute value, this is 0, then this is the shape of this. This is basically absolute value of y1. Okay. Now we know the gradient here. The gradient at this point will be -2. The gradient here will be 1. The problem is that in this point here, we don't have a single upper bound. We have multiple ones. We have -1. We have -0.5. We have 0. We have plus 0.5. We have 1, and everything in between. So all these guys are possible solutions. There are all lower bounds going to this point R. That means that, so subgradient basically tells us, the subgradient of this function in this point is an interval that goes from -1 to 1. Okay? So where a gradient always has a unique solution, a subgradient can have a range or an interval of solutions. So for absolute value of W1, it will be -1 for every point to the left of 0, it will be 1 for every point to the right of 0, and it will be the interval between -1 and 1 for values exactly 0. Okay, now we want to compute this guy, the partial gradient of lasso for Wi. Now this is the sum of two functions, but luckily the sum of subdifferential is equal to subdifferential of, the subdifferential of a sum of two functions is equal to the sum of the subdifferential of these functions if both are convex, which is the case here. This is convex and this is convex, so we can do this. So this means that this subgradient equals this subgradient plus this subgradient. Now we know how to solve this one. This is, we know we have the gradient for this, so we can easily solve that. And we know that the solution, so say that the solution for this guy is Wi is rho I. Right? This is the solution we get from the sum of squared errors. Okay, now that means that we can replace this by Wi minus rho I, and we still have to look at this guy. So it means that if we throw this Wi to the right, this one as well, then our optimal solution, Wi, is the solution we got from the sum of least square error minus alpha times the subgradient of Wi. Okay, we're almost there. So we found this, and we know that the subgradient of Wi for Wi is -1. Sorry, for W smaller than 0, right? 1 for Wi is larger than 0, and -1, 1 for Wi equals 0. So that means that we will split up this solution. So the optimal solution for the weights for lasso will be -1 for cases where Wi is smaller than 0. If this is smaller than 0, then P is smaller than -a times 1. So if the solution of the sum of squared errors is smaller than alpha, or parameter minus alpha, then this is the optimal value for the weight. For the region where this solution, so where the weights of the optimal weights found by least squares are between minus alpha and alpha, this will be 0. And where the optimal weights found by least squares are larger than alpha, we find the solution. If we plot that, we get this function. So again, so this is in function of rho. So this is a function of the weights that are found by least squares. So the green line will be just the identity. So this is just minus x, right? Or rho. The solution for lasso is this red line. So it's 0 between minus alpha and alpha. So assume alpha is 1, then it's 0 in this interval here. If the weights found by the least squares are smaller than alpha, then this will decrease linearly, but according to the least square solution. And if it's larger than alpha, again, this is linearly. Right? This means that if least squares would find a solution would find a weight that is between -1 and 1, lasso will make that 0. Right? So all the small weights of lasso are set, so all the small weights of these squares are set to 0. And only the ones which are larger than 1 or smaller than -1 will still be non-zero in the lasso solution. Right? Ridge, you can do the same computation for Ridge. So this just computes. So Ridge was, again, the least square solution times alpha times the squared of the weights. If you compute that, you will see that the optimal solution for those weights is the weight you find with least squares times the factor 1 over 1 plus 2 alpha, which is plotted here in the dashed blue line. And you can see that Ridge, basically, all it does is makes the weights that were found by least squares smaller. Right? So for every value, for every weight found, so if least squares finds a weight 1, then lasso will find a weight something 0.4, while lasso will make it 0. If we change alpha, we can see what the effect of alpha will be. So in the default solution, every weight between -1 and 1 will become 0. If we make alpha smaller, then this interval also gets smaller, right? So if you set 0.5, then only the weights which used to be between -0.5 and 0.5 will be 0 and lasso. Right? And if we make alpha completely 0, then lasso behaves exactly like least squares. If we make alpha too large, then basically all the weights are set to 0. And we can see the Ridge also makes the weights smaller, but they will never be exactly 0 unless least squares also finds 0. Right? So we see that basically all that Ridge and lasso do is change the weights found by the least square solution. Ridge just makes them smaller, and lasso makes them 0 between -alpha and alpha, and non-zero otherwise. Right? So this explains why we get all these 0 weights. By the way, this function, which looks like this, is called a self-thresholding function. Okay, another way to look at this is to basically plot the whole, because here we look at it relatively compared to least squares. Let's see what happens if we just look at the whole loss function. So here we have the different loss functions. So L2 is this blue curve, and L1 is this V-shaped wedge. This is L0, but we'll not use that. Now, say we have some least squares loss. It will be convex, but where it is exactly depends on the data. And in the direction of this weight W, it finds the optimal solution at weight 0.5. Now, the Ridge loss is basically this black line plus this green line, the blue line. So this blue dot line is basically the shape of this loss function. Okay. So if the Ridge loss is basically the least squares loss plus this L2 loss, which gives us this blue line here. Right? And already we see that the minimum will be smaller. The weight here will be smaller than one found by least squares. If you take the sum of our least squares loss plus the L1 loss, then we get this wave function. So it goes like this up till 0. That has this like dent, and then it falls out again. Right? And we will see that in this case, yes, the optimal solution for this function is 0. Right? So what happens if we change the alpha value? So if we make alpha small, we can see ultimately they will become identical, and least squares Ridge and Lasso will all be the same. If we increase alpha a little bit, we can see that both Ridge and Lasso make the weights smaller. If we do a little bit more, you can see they become smaller, and Lasso makes the weights smaller faster than Ridge. But then we end up in this point here. So after some value of alpha, the weight will be 0, the optimal weight will be 0, and it will stay 0 from then on. And so once it gets in this minimum, it will of course stay 0. Right? So if we plot the entire loss function, we can see that Ridge will also always get smaller weights, and Lasso will get even smaller weights, and they are likely to be 0. This is in 1D. If you would plot this in 2D, it becomes a bit more complicated, but say this is 2D, so we have W0 and W1. The loss function is now this convex contour, so it's a 2D function, so we can only plot the contours here. This is the optimum, the lowest loss. Let's say that the L1 component is, or L2 component is 1. Then if we have a value for L1, any value, because the sum of this weight plus this weight has to be 1, because the total loss is 1, then we will end up at some point according to this diamond. For L squared, because it's the sum of squares, it will end up on this circle. So it means that the optimal solution according to L1, given that, for L2, given that the loss is 1, will mean that it finds this solution. And this solution here you will see that this will almost never be 0, because it's such a, because this is convex and this is convex, it's very unlikely that this will ever be 0. While if you look at the L1 loss, it's very likely to be 0. That, well, one of these will be 0, right? So in this case, W0 is non-zero, but W1 will be, well, the solution we find here cancels out basically W1. Right. Finally, we also can imagine loss functions which are in between. And one of the most well-known ones is elastic-net, which is shown here by this red curve. So it's a combination of L1 and L2. It looks exactly like this. So it has both L1 and L2 loss. It still has our parameter alpha, and it has an additional parameter rho, which is the ratio of L1. So if L rho is large, then the influence of the L1 loss will be large, and of the L2 loss, minus rho, will be small. If rho is exactly 1, then this will cancel out, and then this will be 0. And then it behaves exactly like Lasso. If rho is 0, then this will be removed, and we end up, this will be 1, and we'll end up exactly with Ridge. Right? So elastic-net allows us to set a threshold which trades off between L1 and L2. What this buys you is that you can still learn sparse models by setting the rho large enough. while still maintaining some of the regularization benefits of L2. One example is that if two features are correlated, so if feature 1 goes up, feature 2 goes up as well, Lasso will likely pick one of these at random. Right? So if you have a data set and there's two features and they both change in the same way, then Lasso will remove one of these from the model. And sometimes you don't want that. Right? And then you can use elastic nets to make sure that you keep both. Now, elastic net, because it has this absolute value again, can be optimized with coordinate descent rather than gradient descent. And finally, you can imagine that you can think of odd loss functions like this, right? And yes, there is actually a plethora of different loss functions you can use. Some of the ones which are very good to know about are these. So one of them is Huber loss. So Huber loss is quite simple. It's shown here in black. It will be the same as the square loss up to a value epsilon. And after epsilon, it will have a linear penalty. So it becomes linear. Right? So it's for small weights, it will behave exactly like the square loss. And for larger weights, it will be linear. The idea here is that it's more robust against outliers. So say you have a function which fits some points, but there's one point which is somehow an outlier. It could be noise. For every reason, it's an outlier. That means that this will have a very large residual. Right? The loss here will be very large, which means that the loss will be very, very large. Right? So this one point will have a very large effect on the weights, and we may end up with a function that looks like this, because this one point is kind of pulling the weights up there. So the function goes like this, and it doesn't match the data anymore. It's this one point is kind of well, leading to a suboptimal solution. It's according to loss function, it's good, but in practice it may not be so good. Right? So to correct for this, we can use a Huber loss, which will make the influence of such an outlier much smaller than the square loss. Another thing you can do is the epsilon insensitive loss function. So this one will make the loss exactly 0 in red here. Will make the loss exactly 0 up to a value epsilon and then linear after that. Right? The idea here is that you want to find a linear function so that the maximum loss you find is epsilon. Right? So basically you want to find the function f here so that no error is larger than epsilon. And you can do that with this loss function. Right? So there will be, if a point is within this boundary, there will be 0 penalty, and only when it's outside this boundary, it will get some penalty. Okay. This is also known as support vector regression. Right? It's the same idea of having like a margin in which there's no error, and outside there is a large error. So if you want to try this is called support vector regression. It's in a circular. You can also use the squared epsilon insensitive, and that basically looks like this. So it will again be insensitive up to a point epsilon, and after that point it will behave in a squared way. So it's like this. So any of these you can use. So squared epsilon is, well, you can see this as kind of a least squares SVM solution. Depending, if you want to have a solution which does not fit the data points exactly, but has sort of a guaranteed maximum error, you can use one of these. Now, all of these can be solved with stochastic gradient descent. And if you want to do that, you can use the SGD regressor in scikit-learn and then use the loss function that you want to use.